Hi all, this is my video number 10. In my previous video number 9, I have discussed a couple of theorem related to the sequence, the uniqueness of the limit of the sequence, the convergence, the Cauchy sequence, and so on and so forth. Now in this video, I will give you some example as well as some of the properties of the limit of sequence. Right, so let's look at the example first. First is that we consider that sequence. We show that this sequence 2n over n factorial converge. Now, how to show the convergence of the sequence? First thing, we need to show either the sequence is decreasing or increasing, and we need to find the bound for that sequence, because if the sequence is decreasing, monotonically decreasing or decreasing and bounded, then we can conclude that the sequence converge. That one thing you can do. The other thing is, of course, you can find limit and so on and so forth. So first look at the to solve this, first we look at the monotonically increasing or decreasing sequence. Increasing or decreasing sequence. Okay, so to do this, we just look at the ratio un. Okay, before that, for the increasing sequence, we have what? We have this kind of sequence, so which means un is less than un plus 1. Right? For the decreasing sequence, we have what? Un greater than un plus 1. Okay, you can take equality, no problem. Now, I can write this first thing as one of the approach that I have discussed in the previous video, if I'm not mistaken, video 9 or 8 something. Or you can also show that un over un plus 1 is less than 1. You just divide by un plus 1. Or for this case, you can also show that un over un plus 1 greater than 1. Or you can put un plus 1 over un less than 1. You can manipulate those equality. All right. So let's come back to this. We have those sequence. Now we want to show this sequence either increasing or decreasing monotonically. All right. So if we use the ratio between those two, so what we have is that, so let's say you have un. If you use un plus 1 over un, you can do that as un plus 1. If you use un plus 1, so what we have un plus 1 over un greater than 1. Or you can also use un plus 1 over un greater than 1. They are similar. Okay, if I write like this, so this will give you 2n plus 1 over n plus 1 factorial, multiply, because we divide by un, so which means you just put it upside down, then you got n factorial over 2n. Alright, so that will give you, so we have those 2n that cancel out n, then we got 2, and here we have n factorial, n plus 1 factorial. What left is just n plus 1. N factorial can cancel out, because you can write n plus 1 factorial as n plus 1 n factorial. Then this factorial cancel out with that factorial. What left is n plus 1. Alright? And this definitely for n equal to 1, you got 1, n equal to 2, then so on, you got less than 1. So this is basically less than 1 for n equal to what? 1, 2, 3, 4, and so on. Okay, so therefore if un plus 1 over un less than 1, we have this case here, right? Which means our sequence is increasing. Is it increasing? Yeah. un plus 1. Yeah, that's correct. So our sequence is increasing. Un plus 1 is greater than, un plus 1 is greater than, I think this is increasing sequence, right? Increasing sequence. Yes. un plus 1. So un, for this case, un plus 1, if I write this un, if I write this one un plus 1 over un, that gives you less than 1. Alright, so we have, okay, this is decreasing sequence, sorry, decreasing sequence. Okay, so that's the first part you need to show. The second part is show that the this sequence is bounded. So to show that this sequence is bounded, boundedness of the sequence, we need to find n such that the magnitude of un less than m. So what is the number m? So in this case, absolute of un, that gives us 2n over n factorial. Since n positive, this cannot be negative, so we can write this as a 2n over n factorial. And in this case, definitely 2n as you compare to n factorial, yeah, 2n as you compare to n factorial increasing much faster than 2n. Yeah, n factorial increasing much faster than 2 to the power n. So which means this is less than n factorial over n factorial. That gives you m. So this so this is your m. Alright, I hope you can understand, especially how to choose that part there. Alright, how to manipulate that part to get the right hand side. This is the right hand side as compared to this. The right hand side greater than to the left. Oh yeah. Now with this two assertion that we have shown the this sequence monotonically decreasing sequence, and as well as it is bounded. So therefore we can conclude that this sequence un over n factorial is converged. Is convergent. Convergent sequence. Is a convergent sequence. Now that's a first example. Let's look at the other example. My second example. So let's say we want to determine the limits n goes to infinity ln n over n factorial exists. How do we do that? Now, if you look at this expression, that limit, that function, that okay, that the sequence, if we make it n goes to infinity, and the denominator and as well as numerator, denominator as well as numerator goes to infinity, what we have the form of infinity over infinity. What is this? It is undefined, yes, but what is this? This is what we call as a undefined, undetermined form. Yeah, undetermined form. So for the undetermined form, we can use what? We can use L'Hopital rule. How do you pronounce this thing? Some say L'Hopital rule, some say L'Hopital rule. Just pronounce whatever you want, but I also don't know how to pronounce the correct pronunciation for that. Just I call it L'Hopital rule. Alright, so what is L'Hopital rule? L'Hopital rule is that if you take a limit, first limit goes to have a undetermined coefficient, undetermined form, then we need to differentiate those and differentiate again and differentiate again until you get some result. So for example, if you want to find the limit of n goes to infinity, let's say fn over gn, where we have the undetermined form, infinity over infinity, then you can differentiate this, or 0 over 0 you can also use. Okay, you can differentiate this. That gives you limit n goes to infinity f prime n over g prime n. Alright, and you can proceed this until you get something. Okay, so now bear that in mind for this example here, as we have undetermined form. So what we can do is just differentiate those. So okay, let's do it. Then we have the limit n goes to infinity. We have ln n over n, yep. So that gives you undetermined form, because as n goes to infinity, that ln n goes to infinity, as well as n goes. So we have basically infinity over infinity. Of course, n goes to infinity much faster as compared to ln n. And we can write this, differentiate those. You got ln limit n goes to infinity. So if differentiate 1 over n, you got differentiate ln n, you got 1 over n. Okay, differentiate n, you got 1, and then you just take a limit. This is easy. You got n goes to infinity, 1 over n. That gives you 0. Okay, so remember that when we take a limit, we have undetermined form. Then we can use L'Hopital rule. Even for a function as well, you can use. Another example. We want to find a limit, if it exists, n goes to infinity, 3n cubed over e2n. Okay, so again, if you look at the form, we have infinity over infinity again. Alright, or of course in this case exponential grows much faster as compared to 3n cubed. Alright, so but still we have infinity over infinity, so we can use L'Hopital rule again. So if you use L'Hopital rule, then this equal to limit n goes to infinity. We differentiate the numerator, so we have 9n squared. Alright, over we differentiate denominator, we have a 2 to the 2n. Alright, and then still you have infinity over infinity, and then we differentiate again. That will give you limit n goes to infinity. We differentiate those, you got 18n over 4e2n. Alright, still we have infinity over infinity. Differentiate again, so we have, this is limit n goes to infinity, so we have 18 over 8e2n. Alright, now if you take the limit of this, of course the numerator free of n, whereas the denominator we have the exponential n of order exponential. Alright, so which means that goes to infinity very fast, whereas the numerator fixed 18, just a constant. So which means this give you 0. So that you got the solution. Alright, so I have those examples. Now, what about this? If you want to find the limit n goes to infinity, set n equal to 1. How do we do this? Can I leave this to you to think of? Let me give hints. Then I leave it to you. You can show that this is equal to 1. No, it's not difficult. First thing, when you involve a set like this, to the set of 1 over something, so the best thing is we choose or we use log. Yeah. For example, in this case, this particular case, I will let something y, say for example, equal to 1 n 1 over n. 1 n over 1 over n is that set n. Then from there you can take log of those, then log of y, or you can use ln if you want. That gives you 1 over n log n. Okay, so if you take a limit for this, you take a limit, we need a limit there, and then this is should I write this? No, this is part of that. Then we take a limit of those, n goes to infinity, log y, we means we take a limit of this, n goes to infinity, 1 over n log n, and then you can proceed the rest of it. Then you can show this is equal to 1. Okay, log is not equal to 1. This will give you 0, but then when we anti-log, that give you 1. Okay, so that's a couple of examples that I can share with you. Now let's go to some of the laws or of the properties of the limits. Okay, and I will prove some of them, or maybe 1 or 2, but the rest you do it yourself. Okay, first look at the theorem. Okay, so let the limit of n goes to infinity, this is equal to, let's say, u, and then limit of n goes to infinity, let's say this equal to v. So in other words, we have two convergence sequence. Yeah? We have two convergence sequences, un and vn. So therefore we have then, alright, then we have first properties is that the limits of n goes to infinity, un either plus or minus vn. So we have this equal to a plus or minus, sorry, u plus or minus v. Okay, so which means if un plus vn, we take a limit, then it's converged to u plus v. So if we take un minus vn, take a limit, then it's converged to u minus v. So that's the first properties. The second properties is that we take a limit, n goes to infinity, un vn is equal to uv. Alright, we multiply of those two sequence, we take a limit, then it's converged to the multiplication of the limits. Alright, and then the third properties, that we take a limit, n goes to infinity, we have un over vn, this is equal to u over v, provided that v cannot be 0. Okay, for the proof, I just prove the first parts, positive, plus, un plus vn, and then the rest, you can try yourself, but it's still not quite easy, but the step is similar, but you need to do some manipulation to the sequence. So let me prove the first part first. Okay, so proof of first part. That's what we want to show. Given those things, okay, given limit un equal to u and limit vn n goes to infinity equal to v. Okay, from this, the given convergence sequence, all right, so what we can have, we can use the definition of the limit. Okay, let me give in general. What is the definition of the definition of limit of the sequence, which is given any epsilon positive, you can find n positive such that the difference between the n term of the sequence and the limit less than epsilon for all n greater than n. So this is, in general, we have those sequence. Okay, so let me write those. Limit un equal to u for n goes to infinity. Yeah, u if you put L here, this is L, and so on and so forth. That is just a number there. Okay, so in general that we have. Now in this case, so that's what we have, and we want to show this. Okay, so from the definition, what we begin with the sequence itself, limit. In this case, our sequence is un plus vn. So we take plus. Minus is easy. You just do for the minus. Okay. Okay. Now, from the given those things, given that, so from limit un n goes to infinity, this is u. Okay. We apply the definition. So given any epsilon positive, we can find, now we have 2, so let's consider n1 positive, such that the difference un minus u less than epsilon over 2 for all n greater than n1. The reason why we choose epsilon over 2, here in this case epsilon, because it's just one one sequence. Here we involve two sequences, so we choose epsilon over 2. The reason will become obvious when we come to the when we manipulate those sequence later on. Now, then the limit n goes to infinity vn equal to v. This is also given. Yeah, from the given convergence sequences. Then again, using the definition for the same epsilon, okay, you can find n2 positive such that vn minus v absolute less than epsilon over 2 for all n greater than n2. So what we have here, we have n1 is here, 1, 2 here, for example, or you can put n2 here, n1 here, we don't know which one, but if you choose any n bigger than between these two, so it's automatically satisfy the other one. Okay, if we choose n greater than n2, then automatically satisfy n1 because n1 less than n2. Or otherwise, if n2 on the right, n1 on the right side, we choose n greater than as n1, then definitely automatically satisfy the for n2. So for that reason, we choose the maximum. Okay, choose maximum between n1 and n2. So let's call this as n. Okay, that's what we have from the given sequence that we want to prove, which is the addition of two sequences. So let me use other paper. Yeah. So we have un plus, for minus, I leave it to you as an exercise. It's simple. Vn, that minus un u plus v. That the limit on the right side. Okay, so you can write this as a un minus u plus vn minus v. We just rearrange those things, and then we can use the triangle inequality. So that gives you less than or equal to un minus u plus vn minus v. Okay, now you can choose from here. This is okay. Now this is the reason why when you come to here, the reason why we choose here epsilon over 2 and here epsilon over 2 becomes very obvious. Alright, so in this case we want to show this equal to less than epsilon, so we choose this one less than epsilon over 2, we choose this one less than epsilon over 2. So what we have here, this is less than epsilon over 2 plus epsilon over 2. This is equal to epsilon. We have chosen what n is, which is n is maximum between n1 and n2. So therefore we have the limit of un plus vn, n goes to infinity. This is equal to u or v or u plus n, u plus v. Yeah, u plus v. Now, for the negative, you can do that. You can also prove the, let's say the second part. I give you the idea for the second parts. We want to prove the limit n goes to infinity. Let's say un vn is equal to uv. Okay. Again, we begin with how to manipulate those things. Given epsilon positive, then we can take those things. Now we need to find those n. As I mentioned, I will not going to prove in detail this thing. I just leave it to you, but I give you the idea how to do that one. So we have un vn minus uv. Now this is the crucial part. How can we split those un and vn and u and v? Okay, so what we can do here, you can write this equal to, all right, so we have un vn. Now you can use add and minus, the same thing. So minus, I choose un v. So we minus that one, we plus again un v. Yeah, the limit you just multiply with the sequence you multiply with the limit of the other one. Alright, you can choose v, uv, uvn, you can. So minus uv. Then from there, this gives you can factor out un here, un, Vn minus V. This one you can factor out V plus V. What left is Un minus U. Alright, and then you can use the triangle inequality. This is less than equal to Un Vn minus V plus V Un minus U. Okay, this is multiplication of two sequences, so this is just equal to Un Vn minus V plus V Un minus U. Alright, and how to do what to do next? See, we know that Un is convergence sequence. Un is a convergence sequence. Since Un, that sequence, converge to V, I wrote like this, converge to V, because the limit, we take a limit from our assumption that that goes to V, which means Un is bounded. So Un is bounded, so we must less than some number m, because it is bounded. Converge, the sequence converge, then it is bounded. Then for V, no problem, because just a number, to just take a positive. And then I think that's all. So what we have now, this will give you, from there give you less than, so we have m Vn minus V plus, that one is equal to V Un minus U. Okay, now from the definition, we have Un goes to V, U, so which means given any epsilon positive, we can find N1 positive such that here Un minus U less than. Now here this is the choice. For Un, we need this part here because we have two terms. Basically what we want is epsilon over 2, epsilon over 2. Alright, but we have this constant in front, the V, as well as here we have constant M for this case. So we choose this is epsilon over 2V. So that when we plug in there, those V cancel out with V. What left is epsilon over 2. And this one, so we have this, and Vn goes to V. That gives you, for the same epsilon, we have exists N2 positive such that Vn minus V less than. Now here we have a constant M in front, so we need to choose epsilon over 2M. So the M cancel out, what left is epsilon over 2. Now you have 2M again, as the previous case. We have N1 here, we have N2 here. We need to choose the maximum between those two N, so that it satisfy, when we choose N, satisfy the other case as well. So for this case, we choose, because there exists N, which means we need to find what N is. Now, by choosing N equal to maximum between N1 and 2, alright, and then the rest you can proceed. You just need 1 or 2 steps, 2 lines to complete the proof. Okay. Next, you can prove the third one. All right. So I think for this video is enough. I'll stop here for today. Enough for, we have a couple of examples. I begin this video with a simple couple of examples, and then continue with the proving those two. We have three properties, right? And then I prove one of them completely. Then I left the other one, I prove halfway. Well, 3/4 basically. And then the other one I leave it to you as an exercise. Please do, okay? Please do. So I think that's all. I stop here for this video. See you in the next. Bye bye.